We're now beginning Chapter 3 on binomial coefficients and Pascal's triangle. And we'll begin with Section 3.1 on the Binomial Theorem. The Binomial Theorem was discovered by a Persian poet and mathematician, Omar Khayyam. He lived approximately 1,000 to 1,100 years BCE, so quite a long time ago. What does the theorem state? It states that if you take two variables, x and y, add them together, and then raise x plus y to the nth power, then what you get is a sum of terms of the form x to the n minus 1 times y 1, x to the n minus k times y to the kth power, etc. And the coefficient in front of the term that has k copies of y and n minus k copies of x is n choose k. So x plus y to the nth power is n choose 0 times x to the nth power, and secretly there's a hidden y to the 0th power here, plus n choose 1, x to the nth minus first power times y to the first power, plus dot dot dot, all the way down to n choose n. There's a secret x to the 0th power here, times y to the nth power. Okay, so in this formula, we have n choose k in front of the term that has y to the kth power, and also x to the nth minus kth power. N choose k, we often refer to it just as n choose k, but another name for it is the binomial coefficient, and it's coming from the Greek word binom, which means two terms. In this case, the two terms are x plus y. So that theorem is a little abstract. Let's look at some examples. Let's start at the case n equals 1. X plus y to the first power, that is just indeed x plus y, which if you wanted to, you could write as 1 choose 0 times x plus 1 choose 1 times y. More interesting is x plus y squared. You can multiply that out to get x squared plus 2xy plus y squared. Or 2 choose 0, which is 1 times x squared, plus 2 choose 1, which is 2 times xy, plus 2 choose 2, which is 1 times y squared. By the time you get to x plus y cubed, it's not too much fun to do this by hand anymore. If I wanted to do it by hand, x plus y cubed, I'd take the x plus y and write it next to itself 3 times. To multiply this out, why don't I multiply the last two terms together first? I get x plus y times what I had in the line above, x squared plus 2xy plus y squared. And then when I multiply this out, if I combine like terms, you'll get x cubed plus 3x squared y plus 3xy squared plus y cubed. And that is equal to what our theorem says it should be, 3 choose 0 or 1 times x cubed plus 3 choose 1 or 3 times x squared y plus 3 choose 2 or 3 times xy squared plus 3 choose 3 or 1 times y cubed. Now nobody wants to compute x plus y to the 4th or x plus y to the 5th by hand, and that's the value of this theorem. You don't need to compute those by hand. You can just write down what this theorem says the answer should be equal to. Let me give you a combinatorial proof or explanation for why you should believe this theorem. When we take x plus y and raise it to the nth power, that's of course just the same as taking x plus y and multiplying it by itself n times. Now, if you want to figure out how many terms of the form x to the n minus k times y to the k are you going to have at the end, think of it as follows. So how many times, when we multiply this out, how many different ways can we get x to the nth minus kth power times y to the kth power? Well, when I multiply this out, I have to go through and choose exactly k copies of y to get my y to the kth power. Now, out of these n terms, I'm either choosing the x or the y from each one. how many different ways could I choose k y's out of these n terms? That's exactly n choose k. So that's where this coefficient n choose k is coming from. On the term that has y to the kth power, I need to choose k of these x or y's to be y. The remaining n minus k's will be x's, and hence the coefficient, the number of ways I can get y to the kth power, is indeed n choose k. So for example, how many ways can I get y to the nth power? Well, out of all these n terms, I need to choose y every time in order to get y to the nth power. So I need to, from each of these n terms, I need to choose n different y's, and so there's only n choose n, or one way to do this. How many ways could I get a term of the form x to the first power times y to the nth minus first power? Well, out of these n terms, I need to choose y n minus 1 times, but from one of these terms, I can choose an x. It could either be this first term, the second term, or the last term. So the number of ways to choose n minus 1 y's out of these n terms is n choose n minus 1, or n. All right, so that explanation takes a little getting used to, but try it out and ask me if you have questions. We're now going to do a couple examples using this theorem. So we're going to use the binomial theorem to prove that n choose 0 plus n choose 1 plus n choose 2 plus dot 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 plus n choose n is equal to 2 to the nth power. This is a formula that's already come up for us before. Remember, this was theorem 1.8.2. The way we proved this before is that we said that on the right side, we're counting the number of subsets from a set of size n. A set of size n has indeed 2 to the n different subsets. On the left side, we're counting the number of subsets from a set of size n, just in a different way. We're counting first the subsets of size 0, then the subsets of size 1, then the subsets of size 2, etc., and finally the subsets of size n. Since these two sides are counting the same thing, the number of subsets from a set with n elements, the two sides must be equal to each other. However, this theorem, this formula that we had before, is an immediate consequence of the binomial theorem. We just need to choose x and y creatively, plug in specific values for x and y, and this formula will pop out. And if you think about it, a choice that you can choose for x and y is just choose them both to be 1 in our binomial theorem. And then x plus y to the n is just going to be 2 to the n. And all these terms of the form n choose k times 1 to some power times 1 to some power just become n choose k. And so on one side, I have n choose 0 plus dot 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 all the way up to n choose n. And on the other side, I have my 2 to the n. So the explanation for this example was, in the binomial theorem, choose x and y both to be 1. And so then you have 2 to the n, that's just x plus y to the n. I'm using the binomial theorem. X plus y to the n is this long sequence here. And 1 raised to any power is just 1. So I can remove all these 1 to certain powers and just get the sum of all the binomial coefficients as desired. So that's very nice. This is a formula that we had seen prior, and we can also prove it pretty easily using the binomial theorem. So it's saying that the binomial theorem is quite strong. Another example along these lines is we're supposed to prove that n choose 0 minus n choose 1 plus n choose 2 minus n choose 3 plus dot dot dot, the sign keeps alternating until we get to n choose n is equal to 0. So the difference here is that we have minus signs alternating on half of the terms. So we can also prove this using the binomial theorem. We're going to choose x and y to cancel out. We're going to choose x to be 1 and y to be negative 1. So a fancy way of writing 0 is just 0 raised to the nth power, or 1 plus negative 1 to the nth power. I've plugged in x equals 1 and y equals negative 1 at the binomial theorem. And then the binomial theorem tells me that x plus y to the nth power is all these binomial coefficients times certain powers of x and certain powers of y. So in front of n choose 0, I have negative 1 to the 0th power. In front of n choose 1, I have negative 1 to the first power, or y to the first power. Next to n choose 2, I have y squared, or negative 1 squared. Next to n choose 3, I have y cubed, or negative 1 cubed. When I take negative 1 to the 0th, first, second, third power, that just gives me plus, minus, plus, minus. So I have n choose 0 minus n choose 1 plus n choose 2 minus n choose 3. The signs keep on alternating until I end at n choose n. Okay, this might look unfamiliar. However, we've actually seen this before. So take the negative terms, the negative n choose 1, the negative n choose 3, the negative n choose 5, and move them to the other side of the equation. What we're left with is n choose 0 plus n choose 2 plus n choose 4 plus n choose 6 plus dot 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 is equal to n choose 1 plus n choose 3 plus n choose 5 plus dot dot dot. What we have on the left is the number of subsets of even size from a set of size n, and what we have on the right is the number of subsets of odd size from a set of size n. We actually proved that earlier in the class. This is equivalent to the statement that a non-empty set has the same number of even subsets as odd subsets. Okay, so that's the end of the new content on the binomial theorem. It takes a little getting used to, but we'll practice it on homework. I want to end with one example that uses the binomial coefficients in a pretty minor way, but it's a fun counting problem. So the question is as follows, 3 parts, and we'll start with part A. How many ways can you place 8 rooks on a chessboard so that no 2 rooks attack each other if, part A, all of the rooks are identical? All right, so in chess, a rook attacks either along its column or along its row. So if I want to place rooks on this chessboard so that no 2 attack each other, that means that each rook needs to be in its own column and in its own row. Now in part A, all of the rooks are identical. So if I take these 2 rooks and swap their positions, that's not changing my configuration. So we need to count, how can we place these rooks? How many ways are there to place these rooks so that no 2 rooks are in the same row and no 2 rooks are in the same column? The way we're going to organize this count is column by column. We know we need exactly 1 rook in each column. So we're going to choose first which row is the rook in column 1 in. Next, in column 2, which row is that rook in? Next, in column 3, which row is that rook in, etc., and keep on going. So for the rook in column 1, we have 8 different choices of row in which that rook could be. Once we've chosen that row, for the rook in column 2, there are now only 7 remaining rows where that rook could be. Once we've chosen those first 2 rooks, for the third rook in column 8, there are now only 6 remaining rows in which that rook could be, etc. And so the number of remaining rows keeps decreasing by 1 as we choose more and more rooks. And you can see that the total number of choices we have is 8 times 7 times 6 times 5 dot 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 times 3 times 2 times 1, because we have 8 choices of row for the first rook, 7 choices of row for the second rook, 6 choices of row for the third rook, dot dot dot, until we have only 2 choices of rows for the 7th rook, and the row of the last rook is determined by the choices of rows for all the others. So the answer to part A is 8 factorial. If all of the rooks are identical, there are 8 factorial ways to place them on a chessboard, no two attacking each other. All right. Part B now asks, what if we have 4 rooks made of wood and 4 rooks made of marble? How many ways can we now place our rooks on the chessboard, given that we have 2 different types of material? So we're going to split this into 2 decisions. First, we need to decide which squares the rooks go on. Then we need to decide which 4 of the 8 rooks are wooden. The other 4 will be marble. So as we just saw in part A, there's 8 factorial ways to place the rooks into locations on the chessboard. That's the first half of the answer. Once you've made that decision, you now need to choose which 4 of your 8 rooks are going to be wood. And there's 8 choose 4 ways to do that. So we've broken this part B into 2 choices. First, we have 8 factorial ways to select the choices of the rooks, the locations of the rooks. Once that's done, we have 8 choose 4 ways to select 4 of the 8 rooks to be wood, and the other 4 will therefore be marble. And we're making these choices in succession. We're first making the choice A, then we're making choice B. We're not making one or the other. And since we're making them in succession, that's why we multiply these 2 numbers together to get 8 factorial times 8 choose 4. If we were only making one choice or the other, we'd add those numbers. But no, we need to choose one of the 8 factorial locations and then one of the 8 choose 4 assignments of material. So for part B, our final answer is 8 factorial times 8 choose 4. Last part of this problem, part C. How many ways can we place the rooks on the chessboard? Again, so that no 2 are attacking each other if, in part C, all of the rooks are different materials. So we have, the rooks are numbered from 1 to 8, and each rook is made of its own unique material. Wood, marble, plastic, gold, silver, etc. Again, let's break this problem into parts. Part A, how many ways can we place the rooks in their locations? And then the second part will be how many ways can we assign our different materials to the rooks? So how many ways can we place the rooks in the locations not attacking each other? Well, as we've seen before, that's 8 factorial. And then how many ways can we assign these different materials to the rooks? The rooks are all different. There's actually 8 factorial ways to do that as well, because we have 8 choices for which rook will be wood, and then 7 choices of which of the remaining rooks will be marble, and then 6 choices of which of the remaining rooks will be plastic, and then 5 choices of which of the remaining rooks will be gold. So in total, we have 8 factorial choices of locations times 8 factorial different assignments of material, and the final answer to part C is 8 factorial times 8 factorial. So be sure in your mind you can keep those 2 8 factorials separate. One of them is counting the number of ways to choose the locations, and the second one is the number of ways of permuting the different rooks, all of different materials, amongst those chosen locations. All right, well, thank you very much for watching lecture today, and we'll see you next time.